Hey everyone, and welcome to the first official episode of the Netram Podcast. Today we'll be kicking it off with a guest that I've been super eager to introduce to everyone. He is the founder and current managing director of Donix Embedded Systems. He is also the executive board member of this Cape Town Space Society. Yeah. He also almost shares the same last name as me, which is pretty cool. So I'm talking about none other than the man, Donovan Martin. Thanks so much for being here, man.
Thanks a lot.
Appreciate it.
Brendon. Great stuff. Great to be here. Knock that over.
So obviously you've got a crazy plethora of cool and interesting stuff. When we first built the space, the first thing I said to myself was, damn, you know who's the best guest to get in here? Donovan. And so just after we built it, I was like, okay, I've got to go over and be like, hey, Don, you got to come on the podcast, man. Yes. So obviously, what exactly is it from when you first started, being much younger in university and stuff? Did you always want to be like electrical engineer type stuff, or where did everything come from?
No, so certainly, I mean, from my perspective, and again, growing up in Kimberley, so not much to do. It's like really nothing. Got you. But from way on, I was introduced to space really by my father. I mean, he was a mechanical guy, automech and so forth. But space and things like that always interested me, pretty much to the point where I would build things from a young age. They blew up most of the time.
A lot of experimenting.
Of course, yeah.
Yeah.
So yeah, I would say from early on,
So your passion was mainly in space then?
Something technical, science, anything involved in science and understanding
science makes sense.
The universe.
Yeah. Okay.
I guess whose isn't.
So how did you end up doing? Okay, your current job at Donix,
right? It's
mainly PCB design and product development. So how did that kind of stem into there? Was it a natural progression?
Well, put it this way: in SA, really, my first passion has always been, like I said, aerospace engineering.
Cool.
And within that area, next best thing is obviously where we are today, where you see us today, R&D. So my background has been in defense. For about 13, 15 years, I was involved in defense projects with various companies, the NAL, Saab, and the likes and so forth. So you get to see some really cool stuff, be involved in some great things. I don't think you get to see anything else outside of the public domain, but...
the stories that we've had before, all this the defense stuff is like,
of course, yes,
awesome. Is there anything you could share that it's like, what was the most exciting thing you did in defense that you could share?
Sure, yes, now that it's, of course, yes. So,
what's your favorite thing to always think about? Like, what's the thing you always come to?
So I guess this should be fine. I mean, it'll be more than 20 years now.
We hope it's fine.
So everyone knows, out in Overberg Test Range, and most aspiring engineers and so forth would generally, love to do some testing over there. So everyone's there really, and most of the world. So it's 2,000 square kilometers of basically secure airspace. And the one time we were testing one of the radars that's on the Corvette right now, and together with some of our cheaters, modified the Mirage F1 and some Pilatus. And I think during that period, it was one of the most awesome experiences ever.
Just to be clear, those are jets.
No, jets. Yes.
Okay.
The Pilatus obviously is a turboprop plane.
Okay.
But generally speaking, we spent some time on modified RX doing some evasive nuclear.
Is it nuclear?
Scratch that.
Yeah.
Evasive missile runs.
Cool.
Where we were looking or using forward-looking radar and flying about 500 to 50 to about 500 feet off the deck.
Jeez.
And it was good fun, It was, and of course, being test pilots in the seat, you sign waivers, of course.
Everything is wrong then.
Yeah, that's not their fault.
But what part did you play in that whole scenario?
So we were responsible for radar development, detection sensors, and again, in the entire equipment, effectively from initialization all the way through to production on the Corvettes as you see them today.
So mainly countermeasures.
Countermeasures. Yeah.
Okay, that's insane. And how long was that for? That period of time that you were doing that for?
Paperwork before we began was about 5 years.
Just paperwork?
Paperwork.
Before any real...
Before any real thing, yes.
Before you picked up any actual...
Exactly.
What?
And that gives you an idea of how pedantic you have to be, to get things right. But at the end of the day, lives are at stake.
100%.
So you want to be sure that when the guy pushes the button or doesn't push the button, things happen.
Even though he signed a waiver, you kind of don't want that waiver to come to pass.
Exactly.
That's insane.
Yeah.
And then you, after that, didn't you used to teach at university and stuff as well? Was that like a period of...
I moonlighted as a lecturer at teaching electronics.
That's awesome, man.
And it was, I think the classes began about 6:30 in the evening. And so it was a double or triple, I can't remember. But I enjoyed it so much, we ended about 11:30 at night.
So you got paid for that? It wasn't like just a...
Yeah, of course. Yeah.
Okay.
Yeah,
and was it electronics or science or...
Electronics, yes. Yeah.
Jeez.
So the biggest challenge normally is bridging the gap between school-going matric leavers and, of course, first-year university students. It's always an interesting challenge. Once you get into your second year, you kind of have the flow and the rhythm. But with first-year students, it is one hell of a job.
I can imagine, because how long is that course for them? That
4
degree,
years.
it's a 4-year degree.
Course, yeah.
I can imagine the first year's don't know what's going on.
Of course not, yeah.
That's crazy. And what year is that?
That was, I think it was 2001, thereabouts. Yeah.
That's cool. So from that, how did you end up doing? Because tell me a bit about Donix. What Donix does development for other companies.
Sure.
Tell me a bit more about how Donix works.
So basically, Donix began or started in 2004 as a consultancy. The idea is what happened initially was that there was a moratorium on military spending back in 2003, I believe it was.
A what?
A moratorium on spending for the defense,
like a talk about
budgets,
yeah.
And many of the guys, you've got very specific skill sets. So when there's nothing to do, what do you do?
Totally.
So then they were snapped up by many overseas companies, the UAE, specifically the UAE, look quite a lot.
Yeah, you were saying.
And you either stuck it out, started your own company, or tried to,
So as a lot of the defense stuff fell away, you ended up just doing your own thing for a while.
And then, of course, bringing what we've learned in the defense, the reliability of products and so forth, into the commercial space. And, that's really where it started, and we're still going strong at that.
That's awesome. What's the coolest stuff you've been doing Donix-wise? What's kind of your favorite stuff to work on? Unless
the stuff that doesn't make money.
Yeah, that's the worst, right? That's the stuff you spend the most time on, and it's stuff for some reason. It's like, what is the so obviously your passion lies in propulsion, aerospace, but you still do a lot of the R&D stuff. Tell me a bit more about. We mentioned at the beginning is Cape Town Space Society. Your relationship. I know you spoke about Dr. Walker.
Yes.
How did that come about?
So around, first of all, I must tell you that in terms of
who's Dr. Walker?
So
first?
Professor Walker, basically, there's Professor Walker and Dr. Walker.
Okay.
So
let's go.
A couple, right? So Professor Walker, most people haven't heard the name before. So he was involved in the Apollo 11 moon landings back in '69, and him and his team developed the world's first laser telemetry system to instrument the distance from the Earth to the moon. And having someone of that caliber in SA, and we tend to see them quite often, it's just an amazing thing. Listen to the stories of someone who's actually been there and part of that. One hears about these stories, the hoaxes, the moon landing hoaxes and so forth.
Yeah.
But, when you get it firsthand, literally from the horse's mouth, it's, delays all that.
To be fair, obviously I've met him as well, and you think about those hoaxes, and then you meet someone who's been there, done that whole scenario, and it's hard not to question it. It's like, of course, yes. It's crazy.
Yeah, so
just pull up this page, Matt. Just a bit about Dr. Walker. So how did you meet him?
Right, around 12 years ago, I think it was. That's when we first met. I think it was because of a project of mine. In fact, a family member of mine knew Professor Walker, and he thought it'd be great if we were to meet because we shared similar interests and so forth. And back then, and even today, one of my passions is actually alternative energies.
Cool. Me too.
Beyond the solar, the wind,
totally,
the exotics. And he got to hear about this little thing I was busy with, and promptly came to see me, and that's really where it started. To spend a few hours testing the unit.
What was the project you're working on? Can you say?
Well, I can, yes, because it's a
you can leave out the details.
Mine, yeah?
But I mean, I would love to be interesting to know what were you working on.
Yeah, so back then, I think starting maybe 98 thereabout, we had a group. I think I mentioned to you. We called ourselves NERD. New Energy Research and Development. So
that's cool.
Yeah, so it was a bunch of physicists and scientists from around the world collaborating. And some people involved with us, like Hal Puthoff. I'm not sure if you know Hal Puthoff.
Sounds familiar, but
yeah, I'll do some checking on Hal Puthoff. You'll
cool.
see
I'll check it out.
who the man was. And to be involved with some people of that caliber was very interesting.
All guys from South Africa?
No, from around the world.
You guys were communicating to do it? Oh, so you weren't all on like one location doing it? Oh, okay.
So there's a core group of guys and ladies that were here in Cape Town. And we used to meet ever so often discussing, radical ideas and so forth, proposing new theories. We actually had a few published in Brazil.
Wow.
I don't think I've showed you the papers yet. Everything starts somewhere.
Yeah.
Like some guy calls something a muon, for instance, it's derived from something. Mm-hmm. So, you're given a set of rules, basically, with the current physics that we know. And up to a point, you decide then what's new, because you'll find that some guys working in two separate parts of the world develop a theory or something and they name it something different.
But it's the same thing.
Ultimately the same thing,
yeah.
It's all in semantics. But what's important is understanding.
Absolutely. And so back to what you guys were working on initially that got Hal's attention.
Right. So, being SA energy is always a thing. So we look at ways of improving energy efficiency around either solid state machines or electromechanical machines. And this has been an electromechanical machine which showed very good promise with high efficiencies, very good what we call coefficient of performance.
Okay.
To give you an idea, the coefficient of performance of a windmill or wind turbine is infinitely high, meaning that for all input that you have to put into the system versus what you get out. We talk about free energy. There is no free energy. Energy is always derived from somewhere, either in a
sun or wind or natural forces.
If you allow the system to regauge freely from a large source, I'll give you an example. Something that's maybe quite simple. If you're standing next to a river with a bucket, and relative to you, this lake is large, the ocean as an example, and I were to pull out a bucket of water, the system, which is the ocean, really regauges the hole that you just pulled out. And for all intents and purposes, it's a large ocean of energy.
Absolutely.
Right? So if you think about one thing, when you rip this bucket out of the water, the pressure, right? I mean, it didn't take you much to pull this out, but the pressure around that area, you're looking at the ocean, and areas around there, it actually collapses onto that hole that you left. And it's a massive amount of force that gets wielded in that space. So when you start thinking beyond those kind of limits, you start letting your mind free to explore ideas.
And that's obviously an example of the coefficient of performance, you're saying?
That's correct, yes.
Okay.
Yes. So at the end of the day, we obviously always abide by very strict protocols to actually measure energy efficiencies, because many times people say, aha, I found the Holy Grail, and it's measurement error. So you have to be sure that you make sure you don't really violate thermodynamics. That being said, though,
the input outs, input in out versus whatever.
But did you know there are 21 variations of that law?
I didn't.
Well, that's just the one thing.
Because we only know like the one or two, the ones that are taught, in
yes, exactly.
standard textbooks.
So, given that, it's our understanding evolves, all of the time and so forth in terms of how we can use or utilize energy. It's changing continuously.
So again, and so the group that you guys are working on, how did it get Hal's attention?
Well, because of the machine, yeah. And again,
had you guys actually built physical hardware that showed promise?
I think you may have seen it at the office, not so.
I might have. You've got so many cool contraptions there. I lose track.
Yeah. Okay.
Matt still hasn't seen some of the stuff that's there.
What am I going to show you?
I always tell him about it, and he's like, I want to go see more. He hasn't even seen the iron propulsion model engine, which we'll get to in a bit. So you're friends with Hal Walker. He lives now here.
6 months of the year in SA, and the other 6 in LA.
Cool.
And I mean, he's 86 right now, but still manages to make the trip up and down. He was just awarded posthumously, not posthumously, awarded the, what was the award? Well, put it this way, he was basically shown the plaque that's in his honor, commemorating his influences during the 69 Apollo missions.
Wow.
And,
that's awesome.
So it's now the cornerstone in history books, which is great.
Which is crazy because I speak about him to a lot of people, and many people have no idea what I'm talking about.
Yeah.
And they're like, to be honest, to be fair, I mean, when you explained to me, I had no idea. But then I just realized how much influence he had on that type of thing.
Yeah, so here's the thing. I mean, we all know lasers.
Yes.
So the guys doing the lasers at the time, they were a bunch of friends, which included Hal. So the laser was invented with him in the vicinity, basically. Put it that way.
But we're not talking laser diodes as we see them today. We're talking lasers with...
We're talking ruby lasers.
Rubies. Yeah,
exactly,
Really, really rough stuff.
But that being said, the one to the moon was extremely powerful.
What was the distance, the measurement they got up to what measurement?
Around about 6 or 7 inches.
Jeez. What's that? That's Harry Potter's wand.
That's, I mean, what's it, 500,000 kilometers to the moon?
That's crazy. But before then, how did they measure the distance?
Well, they didn't.
How would they know how far away it was?
Well, they didn't.
So you just send a man to the moon, but we don't know how far it is. You're just gonna...
Yeah, look, they could instrument it more or less, their gauges, but they needed to know the exact distances because that could actually have an impact on Earth, because now you can actually see the gravitational effect.
Pull.
And so
Absolutely.
forth, and how it changes things on the tectonic plates.
That's crazy.
So
that kind of leads to the topic of the Cape Town Space Society, which I'd love to know a little bit more about. He heads up that with you. How does that work?
Right,
what is it about?
Sure. So again, the love of science and space and so forth. We decided, look, Hal, in fact, their NPO in South Africa called AMAN, which has been around for 27 years.
He was doing AMAN Association in...
That's correct.
In Detroit or something.
In the US as well as in SA, because in 97, he was invited to SA by Nelson Mandela.
Okay.
To actually come and start something right here in the country. Because, as he put it at the time, Nelson seen the kids that were with him, and he said, I want you to make kids like those here. And, of course, it was the promise which he kept for all these years. So one of the great mottos is passing the torch.
Absolutely,
so, they're very on in years right now, so they see, they're always looking for people, assistants, to actually carry on that to the path of knowledge and to younger people. And that's really a passion of mine, the whole teaching thing, taking information across to young people. When you see the light, something lights up, it's something to live for.
So how does it, what does it do now, the CTSS, is it?
That's correct.
What does it do at the moment?
Right. So in the US, there's an organization called the NSS, or National Space Society.
Cool.
And it's a global group where they've got these various chapters around the world. Okay. And what they do is they focus on humanity's progression into space and so forth. And that's really what it's about. So it's taking what we have on Earth and actually replicating it in the universe, because we're becoming spacefaring, or a spacefaring civilization.
Soon. If SpaceX keeps it up.
Yeah, and of course there's a few other things on the other side.
I can imagine, yeah. That you'll tell us more about later, but yeah.
So, and of course, when we were in LA with the kids, we went to the International Space Development Conference. So there were 3 kids, Chantal, Skylar, and Dean, and we presented our ion drive concept model. Mm-hmm. And they were so impressed. We became the star of that show. Now, bear in mind, you've got all of the universities there, right? So they've got these massive rigs with their rocket propulsion. And I mean, there's all kinds of. Jeff Bezos was there, kind of floating about.
Oh, you were saying.
Yeah, the kids,
that's crazy.
And obviously, we had gentleman, I forget his name, Buzz Aldrin, right?
He was also running around there.
He was running around.
Yeah, you were saying.
So and gentleman Dyson, he recently passed away. A very, very, very good theoretical physicist.
Okay.
What is his name? His name is Dyson. But
I'll check it out.
I'll get the name.
Yeah.
But if you do some research, you'll see that he proposed how humanity would change and shift over the years and what would be needed. So they got to meet quite a few influential people, powerful people. I know we got to go to SpaceX, of course.
Insane. I'm super jealous.
Yeah, and look, we couldn't get inside the facility because NASA was busy with a defense project.
Of course.
We were foreign nationals, South African's company, but anyway, that's the way it works.
So, Matt, if you just pull this up quickly, so this is obviously this website for the Space Side. I can't get this right. The Cape Town Space Society. This group of people here, we've got Dr. Walker, obviously, yourself, Nikki, your wife. We've got Scar, who's also in the studio here. And then who else are we looking at here?
What's his name again? Oh, on the left. That's Dean in the center.
Yeah.
And then Claire Murray, to the left of Dean.
Cool.
Or to his right, rather. And then, of course, Dr. Walker.
Dr. Walker and Chantal.
Yeah.
So if any of you are listening and not watching the video of this podcast, if you go to capetownspacesociety.org.za, you'll be able to see exactly what we're talking about. And there's a very cool blurb about what they do and exactly what we're talking about here, explained in much larger detail. So that's amazing. The only thing is that the other day you were telling me about Space Ops, right. And that is another conference that happens once a year.
That's correct.
And apparently this year they're bringing it here
for the first time. Yeah, in its history on African soil. So that's quite a feat.
And what is it exactly?
Again, it's a conference for professionals. So the idea is the NASA, the Japanese Space Agency, ESA, all of the big names in space will be at this conference. And, they're showcasing various new technologies and so forth. So you can be pretty sure they'll be headhunting for some good and new young talent.
Absolutely. And you guys are going to be there?
We're still hoping to do so.
When is it?
It's on the 8th, it's between the 18th and the 22nd of May.
Cool.
So it's around the corner.
At the CTRCC, yeah. It's not long ago. I mean, not far away at all.
Exactly. The one challenge we face, of course, is being an NPO, is sponsorship.
Absolutely.
Because being a professional organization, the Space Ops, they charge international rates, so it's rather expensive. So we're getting, the Rotary groups around Cape Town. We get a lot of assistance from them.
Cool.
But we're always trying to get private industrial businesses involved in this, because at the end of the day, it's the youth that comes out of the program that will basically further their careers within the local companies.
Mm-hmm.
That's what we're looking for. And heaven knows we need, greater skills in maths and science.
I know, it's definitely needed. What you were saying, I mean, so you got this conference, Space Ops, and they obviously, is it a conference or is it more of expedition, expo, I suppose, expo of new tech, or?
Well, it's
like, what new tech would they be kind of?
Well, I'm not sure if you're able to bring up.
I can check it out. Yeah.
If you can do that, it'll give you a great idea as to what it's about.
Space Ops 2020, right?
Yeah, and the history of the event.
Okay, I can't pick it up right now, but I will in a bit.
All right.
But yeah, I mean, so it's a pretty costly event, I would imagine.
It is. I mean, for a 4x4 stand, it's about 175,000 rand.
Jeez.
So by South African standards, that's a fair amount of money. And when you're looking at from an NPL perspective, it's even more.
Yeah, because I mean, it's not like you're getting money from. It's like a real income from that kind of thing.
So my drive really, like within Donix, is as a private company, is that I want to see the youth empowered with science technology, really feel the passion for the industry, and really we want to see them roll out in SA. Sure, they can go ahead and study elsewhere, but ultimately come back to the country and actually add value.
So we've
got that capability.
Let's talk about that for a second. So we have this space development kind of conference happening here on South African soil, of sorts. We don't have any such space program. We used to. Do you think we would get back into that again? Do you think does funding need to be allocated to that type of thing? What is your views on like the future of South Africa and space travel or space programs of some sort?
Let me put it this way. My first job was at Hotech, Nel Hotech, which is a space company. And almost in the same year, they shut down.
As you got the job?
Yes, I got the job. So, we got to work with I think there were 3 Cray computers, and that was the only 3 Cray on the continent at the time.
Yes, yeah.
And it was quite unfortunate. I mean, we had the launch vehicle. If you go back in history, you'll see that we had the RSA 2 and 3 space launch vehicles, where we reached apogees of about 400 kilometers.
Jeez.
So, that whole, we had all of it, it was all there. And the future was really looking exciting around that. But then, of course, we signed the non-proliferation treaties, for armaments and so forth, and the programs were shut down.
Had to bury everything or something like that.
That's correct, yeah. Because we were now capable of launching nuclear devices into space. So it was.
And we didn't really have a good reputation at the time.
No, we did not.
For any other reasons. And so back to the question. I mean, what do you think the future holds for that type of
Interestingly enough, I not met him. He's in Greece at the moment. Let me first say, of course, I think we've got a great future as a space-faring civilization or
nation.
Yeah. Because we're in a great location. If we were to launch, I'd say a launch vehicle, we already did the calculations. Durban would be the great place to launch from.
The calculations have been done already.
Yeah.
Why so Durban?
Depending on your launch window that you're looking for.
Okay.
So depending on your orbit type that you want to go for. But you could do it out in Overberg test range as well. But we have that capability. I mean, if New Zealand can have a facility, we certainly can.
Do they have one?
Oh, they do.
For real?
Rocket Labs, yeah.
Oh.
If you look at Rocket Labs, they 3D print their rockets.
What?
Yeah, they 3D print. You're welcome to do a quick check. They've to date launched about 36 American DoD
American DoD stuff.
Yeah.
Jeez. And that's Department of Defense.
Yeah. And they're doing really, really well.
Wow, that's insane. That's the first time I've ever heard that. That's crazy. Okay. But I mean, they don't do any...
No manned launches.
Yeah. But I mean, no one's doing that yet. Well, besides NASA.
Aside from NASA, and of course.
SpaceX is apparently doing it next month.
Yeah, that's where they're heading.
Or May.
With a Dragon capsule.
Yeah. I see they've done a bunch of tests for the emergency cutoffs and things like that. Yeah. And everything.
Look, and the Russians, of course, I mean, they've been doing it for forever. They were the first ones to actually get up there.
Yeah.
So, they're always rough and ready to do things like that.
And then, so they were the first ones, obviously, in space. And then we have America just pouring funding into getting to the moon. Yes. So, and then but then we didn't have anything for 40 years?
Yeah.
Or so. And then we have now the new 2021 or 2022. NASA apparently says we're going back to the moon.
Absolutely, yeah.
What are your thoughts on that?
So, coming back from a military background or defense background, you always get you're privy to a few things that you hear and see. And of course, you can't report on it really. But and I mean, it's not a secret that they're black projects.
No, not at all.
That it's budget allocated massive amounts. In fact, during the Reagan administration, for the entire fiscal year of the country, they allocate, and I think it was something in the order of about just on 80 billion, which is allocated to a certain
Repeat again,
area.
80 billion?
$80 billion.
Jeepers.
And that was in 1 year, in 1988 when Reagan was president at the time.
So that's in 1 year, $80 billion just, what,
remember the period,
goes missing or?
No, it was visible, but in other words, it was spent, but it was spent on black projects.
But I mean, what's the label and on that?
It's just, it's project
you know what I mean?
this and that.
Okay. A project, random name that no one...
Yeah, it's just a top level thing.
Okay, continue.
So you get to see and experience things that tells you otherwise. And there's I think it's the X3B. I can't remember the exact name, but it's been flying around from NASA for some time now. It was since the shuttle was defunct. They then launched this vehicle.
X3B.
Yes, it's a tiny shuttle.
Then they've been using that for what exactly?
For defense projects. No one knows what
the Boeing X-37. No.
X-37.
X-37B.
Yes.
Huh. Air Force's mysterious space plane. You learn something new every day, huh?
It's been running around for forever.
I've never heard of this. I don't understand.
I don't blame you, because media doesn't really focus on these things. They tend to clear the path quite.
So what does this do exactly, Don? What do they use it for that you know of, that you've done the research on?
Well, obviously it's small enough or large enough to carry a single human payload, two people, I guess. In fact, there's a great picture of it somewhere with it landing on the runway or coming down, if you can find that.
Let's go see
an
images.
Awesome picture. Yeah.
That's on a runway. I don't think I can find one that's doing anything else. So they do manned missions with this?
We don't know.
Okay.
But it's large enough. There you can see an idea of the size.
So how does this relate to going back to the moon? Or
right. So Lockheed Martin, our other company.
Yeah, our other company. Yeah. Low key.
Yes. Exactly. They've been involved in space projects for a very long time. We know the B-2 stealth bomber. It was conceptualized and built in the early 80s. And we only found it out about it many years later, and so forth. So there's many projects that run. That's always, from a public perspective, we only get to see it 20, 30 years after the fact.
Yeah.
The same with the space program. There's what the public knows, and then of course is what's internalized in the defense projects, or the black project.
So what you're saying is they're doing it all in private, and then only reveal to the public what they want to reveal, a little bit later on. Okay. Yes. Fair enough.
Yeah.
I'll take it.
Yeah.
So a lot of their stuff is done by Lockheed.
Yeah. Look, as you can see, Boeing is also doing some good stuff, but Lockheed has really taken the lead on some of these things.
They made the F-35s, didn't they?
They did. Yes.
Yeah. There was, I don't know if you've seen, but recently Elon went to an Air Force conference or some kind of Air Force. Yeah, it was a conference of some sort, and he was a guest speaker, and it was just a room full of Air Force pilots. Yeah. And he literally was the man to stand on stage being interviewed, just like this, and he openly said that the days of Air Force pilots are over, and that autonomous warfare will be the future.
Yeah.
Man's got balls. It's like, go stand and say that in front of all those Air Force pilots. But he's got a good point. He says the F-35s are way too expensive. I think it's sitting at 112 billion.
It's crazy.
Or 112 million. I'm not sure. Well, it's something ridiculous.
Yeah, I know. I remember that particular aircraft was, if I remember, it was 5 years late and $600 billion over budget.
Ridiculous.
Yeah,
but that's the most that's the most advanced craft they've got.
Yes. Well, yes.
Yeah. That we know of.
That you know of.
And a lot of them say, currently costs $94 million and $122 million for the F-35B, which is obviously the latest version. Right. They've got like a headset that they put on that allows them to see through the whole craft. They obviously augment the sensors.
That's correct.
They can see everything. So, Matt and I were having this debate. So you've got this plane. It travels X amount of distance. It can only change direction as much as the pilot could possibly handle.
Yeah, because the inertial
force, right?
Correct.
If he had a drone or a autonomous F-35.
Let me put it this way, all right? So we always think in terms of inertia, right? So we're always bound to our current laws of physics, right? But that's always evolving, depending on how you think.
Physics is evolving, or the way we deal with it? The
way we deal with it. Physics has always been evolved. It
is what it
always will be, and so forth. So we're just playing catch up over a long period, or short period at this point. So did you know, as an example, NASA handed out, I think it was $18 or $15 million contract to do a feasibility study of reducing the gravitational field above a launch pad.
Okay.
So that tells you something, that the research that they're investing in is basically not so much going faster, or pulling enough G's, but is to reduce the gravitational constant.
So instead of us trying to overcome physics, we're trying to...
because remember, you can only go that fast before you black out. You'll never go beyond a certain speed. So if you really want to pull some real G's or no G's, then you need to change the way you do something.
That's very interesting, because that brings me to the concept of how we were talking, if in a theoretical means you could generate your own some sorts.
In terms of UFO, because then you're a nutcase.
Yeah, absolutely. You can't use that word anymore.
Exactly. Yeah. So now that the US Navy has come forward and said, look, these things are real, all of a sudden it changes the dynamic. People are coming forward with amazing stories. Some very high profile people in various places that are coming forward with some great stories in terms of, what we've been doing, or what the largest military countries have been doing in terms of this lot. And some of the things are just phenomenal. For instance, the B-2 stealth bomber, we know it's been around for some time, but there are some theories that was going around, I think, in the early or mid-90s, maybe toward the end of the 90s, that a craft operated on principles of electrogravitics. Mm-hmm. Now, that's really the manipulation of gravity field by electrostatics, the voltage.
Got you.
There was a gentleman by the name of Dr. Townsend Brown, who I think I mentioned to you some time ago.
A lot of people might recognize that name if they know anything about
exactly.
this world.
So electrogravitics is actually one of the ways to actually supposedly reduce gravity and so forth. And you can try some various experiments. Many blame it on the ionic effect, ionic wind effect, which is true, it does exhibit. But it depends on how you produce the craft. Frequency is important. There's a whole array of things you have to really match up very importantly and critically to see the result in its purity, because it can be masked by ion wind effect very easily.
Got you, yeah.
But it does exist, and that's just the thing.
So coming back to what I was saying about, what you're saying is overcoming gravitational forces.
That's correct. We have to change the way we move these things.
It's fascinating.
Yeah.
It's fascinating as well that, I'm under the impression that this kind of, it exists in probably black projects of whatever sorts, but then you've got a man like Elon who's pouring, just millions and millions and millions into space programs, but just using generic propulsion that we're all familiar with, just in a very optimized and efficient way,
yes.
Reusability, different fuel that he uses.
Yes.
Why wouldn't he be using?
Well, he
techniques?
Has spoken about it. Electric propulsion. At the end of the day, he is using an electric vehicle, but right now it's the quickest and cheapest way. You think about the evolution of electric vehicles versus gasoline-driven engines. It's easier to build an electric car back then. It's a single. It's an armature, it's a single, and there you go.
Super
off
easy.
You go. Just the batteries was an issue.
Yeah.
But the motor itself was the simplest thing in the world.
Of course.
But
compared to like a normal gasoline motor, it's insane.
Obviously, the energy density in a drop of gasoline or petrol is basically what they see as the big game changer. But that can change. The U.S. Navy is also basically, and we're not sure how good the intel is yet, but they've run this through the patent office. They have released a patent end of last year of basically a nuclear fusion reactor of the size of this table.
What?
That produces 1 trillion watts of energy.
What?
Yeah. So they've also got a new patent that basically states that they've got an inertial drive that they've brought along, and
what's an inertial drive?
It's gravity reduction.
Got you.
So you can make changes, radically different changes without influencing the occupant.
Yeah, anyone inside it's for sure.
They've released the patent. They've come forward and said, this is it. So that's very interesting. The fact that they've done that had the patent office scratching their heads, but it's been put through. So it's there.
But the patent office doesn't actually check that.
Oh, they do.
They have to?
Oh, yeah. That's why you find that any zero-point energy devices are always scrutinized, as heresy.
Yeah, absolutely.
Because
it shouldn't exist.
Yeah, you're violating thermodynamics.
Yeah.
But like I said, if you allow the system to be re-gauged freely from an open loop system, then you can draw as much as you want.
Which blows my mind. Going back to the electric topic, batteries, efficiency of them, obviously with Tesla making huge strides in that field. I was reading an article the other day about, it's been 100 years since we've, is it 100 years? It could be more, since we've gone from every other tech. Look at your cell phone, how insanely improved a cell phone is in comparison, just in the last 10 years, even 20 years, insane, the leaps. Yet vehicles haven't progressed from gasoline engines since 100 years ago, since for the first engine, the first cylinder they used. And in fact, I forget what year it is, but I'm pretty sure California, there was a mandate where California said, you know what, we want to do electric vehicles only, and we don't want to use gasoline anymore. We don't want to burn fossil fuels anymore. And then GM came out with the GM EV1, which is the first electric vehicle, right?
Correct, yeah.
And then, in fact, the state of California, I'm not sure what part of it, was bullied by the car manufacturing companies to...
I think that you've watched Who Killed the Electric Car.
I haven't. That's what I'm getting to. Yeah.
Okay.
Is that what this is about?
Yeah.
Okay, very interesting. Because they released a documentary apparently about it saying Who Killed the Electric Car. I imagine that's probably what it's about.
Yeah. I have that if you'd like to see it.
I would like to see that. Maybe it's on YouTube or something, but
probably is. It could be. I know you could hire it at one stage on DVD. It's like tucked away in the corner, really.
But then there was a second one, The Revenge of Electric Car, isn't there? No? Is that my imagination?
No, I'm not too sure of that.
Maybe that's Tesla's... new bio.
So coming back to the reason why, looking at electric space propulsion or in-space propulsion versus chemical rocket. So, and this brings us to the Vasimer, where it's a propulsion, or rather it's an ion-based or plasma-based in-space propulsion system that is highly efficient, right? So the normal trek to Mars is about 9-10 months, really.
Yeah.
And using the Vasimer engine, you'd be able to get in 39 days. So the round trip is really super. And because what you're dealing with is that...
That is there, right?
Oh, yes. So
spelled it wrong.
So the specific impulse of the Vasimer is very, very high. Chemical rockets obviously are great for having high values of thrust, able to leave the Earth's atmosphere.
Because that's where we need it the most, right?
Yeah. But once you're in space, they become really inefficient. Whereas with electric space propulsion systems, plasma-based systems, you've got a little goes a long way, so to speak. So your ratio fuel to payload can really change dramatically.
So just for the guys listening and people who are watching who are not entirely sure what we're talking about, just explain how this works versus normal rocket-propelled engines, fuel engines, kerosene engines.
So the similarities really at this point is you get a fuel, like xenon, typically, and you have a reaction drive, basically. So it still obeys Newton's laws, You consume a fuel and you have, a exiting velocity, gas. In this case, it's ions. So ions, in this case, obviously leave the engine at massive speeds, And in fact, you could possibly get close to the speed of light, depending on your drive. And at the end of the day, because the thrust is rather low, but your specific impulse or the ejection velocity is very, very high, you'd eventually attain the velocity of the particles
over time,
ejecting. Yes.
Provided you've got no resistive force.
Which there is none in space. Exactly.
So if I had to break it down, you've got your normal rocket engine, which will leave the Earth, and that is gasoline that is ignited. And typically, whatever the gas may be, and then thrust, it gives you thrust, and then it'll get you out of the atmosphere.
Yes.
Right. Whereas Vasimer engines, you would need to ionize a gas. Typically, what is it? They use argon, xenon.
Either will do, and that's the great thing.
Okay.
So it's basically it's a glorified microwave oven.
Yeah.
You're superheating the gas to a few million degrees. It's contained by a magnetic field, and you eject it with high velocity.
Gotcha.
So you think Star Trek, plasma in the cells, it's really the same thing, It's
so you're choosing high voltage.
So obviously voltage and frequency, right, is important. So what you're doing is you're resonating the cavity, much like a microwave, like I said. So you've got your various couplers in the engine that you'll get a cold plasma, and then it gets energized further downstream, and it becomes a hot plasma, very hot, a few million degrees. And obviously then that's contained confined within a magnetic field, much like a tokamak, which is, where they're trying fusion or fusion energy right now. And then, of course, that gets ejected, directed with a magnetic nozzle at the rear end. Now, this is not just science fiction. It's actually being tested on the ISS as we speak.
For real?
Yes.
How?
So, on smaller items. The idea is because the engine can be quite small, right? You can attach it to almost anything. So, if you have an asteroid that's approaching Earth, you can literally fly it out to the asteroid and actually attach it and use that to redirect the asteroid. Same with space debris, large bits of space debris. So they can use this engine for many, many things other than just a primary propulsion.
So you have something that's flying towards the planet or flying towards a certain, in a certain direction. They obviously fly an engine towards it and attaches it to that debris.
That's correct. Yes.
Interesting.
Yeah. And it's quite small. I mean, if the listeners were to look at and research the VASMA, they'll see that technology-wise, it's great. It's working. It's running. And we were fortunate enough to meet some of the developers of the engine.
You were saying,
yeah, at the conference.
And you guys designed a small miniature scale version of this concept?
Yeah, exactly. Yes. It was nowhere near as exotic as the one. We could actually run it in air.
Yeah.
But the idea is you could then see the concept.
And now you could see the concept of ionic wind and all that jazz.
That's correct. Yes. So we achieve about the exit velocity of the ions are around about 2 meters per second, which is fairly high. That's 7,200 kilometers an hour.
Jeez.
Of lithium polymer, 2,000 amp
battery,
2,000 milliamp hour. Yeah, and it runs for about 3-4 days continuously.
Jeez.
So let's just use that as an analogy.
Okay.
So your exit velocity is sitting at 7,200 kilometers an hour, and of a single charge, you can run for about 3 or 4 days at that velocity.
And that's not a lot of power.
No, so the wattage of the system consumes roughly about, and I'll quote because obviously you're running at about 50 kV voltage-wise, but our current draws quite low as expected, run about 80 to 100 milliamps for that system.
So in an ideal world, we get an VASMA engine into space. Do we use just a crap ton of batteries with solar panels, and we just
That's
go?
a good question.
How do we power that?
Yeah, sure. The one thing right now in terms of the VASMA is obviously the power source. That's always been the stumbling block right now in terms of how you want to generate the power to create the plasma source. So there's been various ways of doing it, either batteries, or solar cells, so to speak, or solar cells in space, because you can scale. That's the one thing you can do. You can scale as large as you want to.
Yeah, because there's no restrictions, really.
Exactly, yes. Yeah. So that's the one way of doing it. The other way is, of course, fusion, the holy grail of energy.
Well, now that we have patents for it.
Yeah, and if you look at the energy output, I'm not sure, maybe you can bring it up, U.S. Navy fusion reactor.
So, hey guys, I'm Matthew.
Hey man, what's up?
I'm handling the back end here. I just wanted to find out, up until now, the fusion reaction has always been more energy in than it outputted. So it's never been a sustainable source of energy. Has that changed in a way now?
Actually, what has happened is they've already gone past that barrier, but they could only sustain it for a few minutes at a time before they actually lost.
I see.
They get before they start getting diminishing returns.
Yeah, so they were able to actually achieve that already, that milestone, which is why the Chinese are saying by 2024 they'll have an operational fusion reactor.
Well, if they said it, I'm sure it's true.
Yeah.
They can do anything.
Yes.
I see, I mean, obviously Popular Mechanics even posted about they have a compact fusion reactor.
So it's got the science community up in arms. No one knows what to make of this lot.
Why? Is it because it violates the laws of...
Well, because of the size, for one. It's like I said, it's 1 by 1 meter as an example. And it can generate, if you scroll down on the screen there right now, you will, it may mention the power output, I think. maybe.
Don't see it here.
Yeah.
Maybe it's as a metaphor. Hold on. So they say 1 kilogram of fusion fuel produces the same amount of energy as 10 million kilograms of fossil fuels.
Yeah.
Which is a metaphor, but a very easily understandable one.
Yes.
It's about time. We need to get rid of this fossil fuel thing.
Of course, yes. I mean, it's that's really holding us back as humanity. Really.
It's a joke. I mean, it is. That's the one thing that's irritated me a lot the most with. I mean, we do a lot of R&D stuff as well, and when you're making devices, biggest thing that irritates me the most is, oh, hey, I need a device that sits in the field or does something, but I can't charge it, and it needs to just exist, and it must send me data, and it just needs power forever.
Yeah, exactly.
It's like, how? I mean, batteries are going to last so long.
Yeah, that's why you look at, the 0-point field is now well known. Quantum mechanics entered the game. And in fact, in Germany... A
new players entered the game. Yeah. Carry on.
Back, I think the West still teaches classical electrodynamics, meaning the stuff that you learn, Maxwell, as we know it, with its limited equations, but there's a few other equations where Maxwell actually extended. But
which aren't known?
They were actually normalized because the gains of the equation showed something ridiculous. So what they do is there's a nice little mathematical trick. You can actually just re-gauge the equation and you make the result null, and you just ignore them.
Interesting.
So it doesn't matter how many tricks you do. At the end of the day, if the observation was there, then it means it's still real.
Interesting.
So, all of that kind of stuff. So Germany, as an example, they've introduced in their syllabus QED, which is quantum electrodynamics. So they teach electrical engineering as part of what we know in the West, plus quantum mechanics attached to that, because you cannot divorce the two. It's one and the same thing. You're dealing in the same space on quantum level, subatomic levels, things like that.
So, I mean, back to my point in terms of the power issue. I just hope at some point we will find something that, we don't have to be like, oh, no, I need to charge this device again, 2 days later or something, at least last much longer. It's going to be, it's solving the energy crisis, I feel.
Let me give you an example. Right, so...
Just check your mic there. Just make sure you're still
thank you.
Yeah. Just make sure you're still talking in. Yeah, carry on.
So we all know the Big Bang Theory. That's what's known, right? Or so we think. So there was a gentleman by the name of Nassim Haramein at one point. So he walks into MIT, and there's a great book called Gravitation. It's quite a massive book. And he says, it's dealing with gravity because when you lift this book, you can feel it. It's really. And anyhow, he walks into the classroom, and there's a bunch of professionals, obviously just professors and scientists, and they're going to talk about gravity and the universe. So we know the universe is expanding because of the red shift. We see, it's the Doppler.
The frequency change. Yeah.
So we know the universe is moving apart, away from each other. And on, I think it's page 37, I can't remember exactly. But there's a picture of a balloon, right? And on this balloon, there's pennies, American pennies, stuck on the outside. And as part of the syllabus, they basically teach this to aspiring students, saying, look, this is our current model of the universe. It's expanding, right? And they've got this guy blowing the balloon. So they all see this picture, and he says, look, has anybody really examined this picture, So he says, this is physics 101. You should go back and, just sit down and we'll do the talking. He says, no. He can understand this picture, but if he completes this picture right now, say, takes the picture and he draws a pair of lungs at the bottom, and he wants to know, who's this guy? Right? Because if the universe is expanding, and they're showing, by symbology, someone blowing it up, then surely, because if something's expanding, then something else must be contracting. Because if they're saying it's not, then that's just heresy, because then you're violating thermodynamics.
Absolutely.
So then the room is quiet, because that's what it is. So all of these little examples are popping up here and there to actually support some great claims of energetic vacuum energy. And we know it's there. It's just how we access it. You know, there was a great... sorry, you want to say something?
Carry on.
There was a great experiment back in the 1870s done by... It's called the Michelson-Morley experiment. And I think I may have mentioned that.
You mentioned it once before.
So it's based on laser interferometry. So in other words, you want to see that, assuming that the Earth is basically immersed in an energy-dense environment. Much like if you were driving down a highway and you stick your hand out the car's window, you can feel the resistance that the wind offers, right? So if I use that analogy, and you imagine the Earth immersed in this wind of energy, and if I were to stick my hand out far enough, I would feel the resistance that the energy density is offering. And they had the interferometer, right? And they couldn't detect the shift. And I remember we're back in 1870, right? So it was known in history as the best failed experiment.
Okay, yeah, I think I know about this.
Yeah, they went to prove something, but they ended up disproving it, with the best intention. And Einstein used that as the premise for the theory of relativity to do all of his and all of his work.
Got you.
You must remember, even Einstein said that quantum mechanics was spooky action at a distance.
Yeah. I've been reading a lot about quantum entanglement recently. So yeah.
So one can simplify this lot. Faraday himself said he believes in a very tangible universe. So Faraday, Maxwell, when they originally formulated those equations, they believed in something tangible, right? That's something that wasn't just because quantum mechanics believes that things pop in and out of existence. Now, people struggle with that concept. When you can't quite understand how something can be here today, and it's actually gone, but it's not gone.
But it's also in another place at the same time, all type of things. Yeah.
So it tends to confuse the issue quite a lot. In any event, they believed in the existence of the ether, right? So,
this is where the ether comes from.
Right.
Yeah.
So did you know that American Scientific published in the magazine, I think probably about maybe 8 years now, or maybe 6 to 8 years ago, I can't remember exactly, they quietly brought back the existence of the ether in the scientific domain. Yes. Under a different guise. Yeah, because if you believed in the ether, remember, according to Einstein, space was a vacuum. In other words, there was nothing.
And his theories are more mainstream than anyone else's.
Yes.
So,
fortunately enough, his theories are still holding close to the event horizon, but Newton's is broken down already. So that's it for Newton. And that happened maybe about, I think, toward the end of last year.
Really?
They did some,
Wow.
They basically verified a few things there. So Einstein's next on the list.
He's up for debate.
So it's still holding, but just barely in terms of what they're doing right now. So coming back to how this ether, call it what you want.
What do they call it now?
Dark matter, dark energy.
Is that what they call it now? Dark?
Yeah.
Okay.
Yeah,
I would imagine they would have renamed it of some sorts.
Yeah.
Okay.
At the end of the day, let's think of it as a fluid, energetic fluid, right? That surrounds us all.
Okay.
And I use this one example as well. So you've got the universes are expanding, but our spiral galaxies are always rotating, right? Now, if I were to just use another analogy of, let's say, a 20-liter paint drum. So you've got the stationary paint sitting in the drum, and you're about to stir this lot, and you start stirring this lot, and they obviously the inertia is quite high, until you start getting, you start overcoming the inertia, and you start overcoming the boundary layer friction inside the drum, and this whole thing is rotating quite nice. So it's feeling pretty good.
Yeah, got you.
Now, what that took to rotate a 20-liter drum of paint. Now, let's just use our own galaxy. It's 100 million light years across, and it's spinning. Can you imagine the torque required to rotate
start that
100
rotation?
million light years of stuff?
That's a very interesting concept.
Right. So there's a torque somewhere that's occurring, that's allowing this to happen, first of all. And it's highly energy dense. So coming back to the ether, so there's a professor, and I think he's passed away now, Professor Harold Aspden. And again, you can research him, highly respected physicist. he started his career much like any other physicist. You get taught the same things. And he basically discovered a few anomalies in his career. It's fine when it happens, once or twice.
Yes.
But an anomaly is no longer an anomaly when it occurs ever so often.
Absolutely.
Then it's worth investigating.
Mm-hmm.
So he started with a postulation. He said, look, our hypothesis, he said, so let's assume that the ether does exist. But let's assume also that it's very energetic. How would I prove that? And he had this motor, right? A purely an attraction type motor. And he had, and it's a white paper. You can download it.
I was going to ask. So this information you're saying now, we could go and find.
You can absolutely access it. Yes.
Okay. What would we have to find if we wouldn't do it right now? But if we had to search it, what would it be under?
You first of all search for Dr. Harold Aspen.
Dr. Harold Aspen. Cool.
Yes.
Perfect. Carry on.
And I've got a crap load of his papers.
Okay.
And I can't remember the exact paper, but it was vetted by peers. And again, what's important is obviously the observation. The scientific method demands you do things in a certain way.
You have to, yeah.
And it was followed very critically, right? So how did he do this? Well, so he figured, he's got this motor, right? So he starts it up, and I can't remember the exact figures, so I'm just going to use examples of it. So he starts up this motor, and it takes about 3,000 joules to start up. And he measures it with very, very precise instrumentation and notarizes the results in his lab. And he shuts the machine down and checks that there's no residual energy remaining anywhere and so forth. And he does this within a very short space of time. And he starts up the machine again. I remember he's measured everything and his residual energy is 0, net energy. And it takes around 300 joules to start up the same machine. He figures, all right, first thing you do is question your own measurements and question the instrumentation.
Instrumentation would be your first bet.
Of course, yeah.
Yeah.
So you shut it down and you verify, check the connections, check everything. And he realizes that nothing's wrong. So he powers it back up, 3,000 joules. Gosh, this is really, this is going to get really wild now. So he figured, okay, look, the only difference is the time that he shut it off, it was a longer period, right? And when he powered it back up again, things had settled to quite a zero mean energy. So he figured, what could possibly be happening? So now we go back to the paint drum, which I raised earlier. So assuming that the energy is dynamic, right? And when you have an electric motor, the fields couple into the space around it, right? It's like the Earth's magnetic field couples and changes things around it. So you've got this rotating magnetic field coupling into the ether around it. Eventually, by rotation, assuming that the ether exists and is energetic, it'll couple like a clutch, right? And the outside will rotate with the machine. So you've got inertia around the machine.
Got
right?
you. Yeah.
So imagine I rotate the space around the machine, right? And I stop my machine.
That space is going to carry on going.
That space rotates,
yeah.
Right? So eventually, if I restart my machine within the critical time period, I engage it, and it locks back into the clutch, and it takes less energy.
Less resistance.
To restart the machine. So how do you prove that?
Very interesting.
So what he does is, okay, I've got a great way to prove this. So what he does is, in his lab, he sets up a rail system. So maybe about 10 or 15 meters or so. And on this rail system, he's got the machine standing where it originally was, starts it up within the period of time, observes that it takes 3,000 joules to start, shuts it down, and within 5 minutes after checking the instrumentation, restarts and makes sure that it actually takes 300 joules. And he's able to do this consistently, first of all.
Jeez.
Now, the hypothesis is, if this area of space is still rotating and that area is not, if I move the machine physically from this space, point A to point B, in the same time frame, and I restart it, it technically should take 3,000 joules again, because that space is stationary.
Absolutely.
And he could repeat that every single time.
That's insane.
Yeah. So he's able to move it, and it will take 3,000 joules.
I need to go and find out more about this. This fascinates me. But no, so what year is this?
Oh, this is some years back. I think
I just love it.
80s or so.
You hear all these experiments, all these cool white papers, but it all happened like 40 years ago. It's like we're still sitting here trying to figure out how lithium-ion batteries work.
Yes.
It's insane.
Yeah, exactly.
I think are we out of time? We're getting there. Okay, we go through.
Pretty much.
Yeah, pretty much. I know you're a busy man.
No, well, like I said, it's exciting stuff.
It is exciting stuff. We can talk forever. Donovan, one of the smartest men I know. Thank you so much for
Thanks a lot. Thanks for being here. Yeah, it was great.
And I will chat to you soon.
Indeed.
Cool.
Thank you.
Cheers. Thanks, guys.
Ciao.